Hello students, in this lecture we'll state the Gauss divergence theorem in Cartesian form and solve problem based on it because we don't have proof of Gauss, Green and Stokes theorem in the syllabus. We'll state the all the three theorems: Green, Gauss divergence theorem, Green theorem in a plane, and this is Stokes theorem. Statement only, their statements in syllabus only in Cartesian form, and then we'll solve problem based on that. Right? So the statement of Gauss divergence theorem statement is if f is a continuously differentiable vector function, vector point function or vector function, and S is the closed surface enclosing the volume. This is the closed surface volume enclosing the volume. Closed surface means, what do you mean a closed surface? Means either it is a this volume of the cuboid or rectangular box or sphere, anything closed means all it's closed from all the forces. That is the surface of that. So then the surface integral, this this integral over the whole surface of f vector dot f vector dot n vector ds is equal to not equivalent to is equal to volume integral is equal to volume integral of divergence of f over the whole. So surface integral of f dot n surface over the whole surface is equal to volume integral of divergence of over the whole. They will be equal by cos divergence. Divergence what is from here? Divergence of f, divergence of f, volume of divergence of f. Component of f in the where n is the unit outward drawn normal vector. It's outward drawn. So if the face of the if the faces of face of the uh, face of the surface enclosing the volume is not a smooth function, that will be piecewise smooth. So at each point you have to find the equator n. At each face, if the surface consists of a finite number of smooth surfaces, then you have to find the equator each smooth surface, and then find the surface at each surface, and the sum will give you the surface integral of the whole surface, right? Or another form is normal surface integral of f, normal outward normal of f over the boundary of a closed region is equal to the volume integral of the divergence of f taken throughout the enclosed volume, right? This is the statement theorem. Now we'll solve problems. First problem is evaluate the surface integral of f dot unit vector n ds with the help of the Gauss divergence theorem for the function f is equal to 6z iota plus 2x plus yj plus x into k taken over the region are bounded by the surface S of the cylinder. The cylinder x square plus y square to 9 included between x is equal to 0, y is equal to 0, z equal to 0, and z equal to the volume this z equal to 8. Means it is in the first octant, this plane, this is yz plane, this is xz plane, this is xy plane. Xy plane, this they are equal to 0 and z equal to. This is the first octant. This sphere, you have to this is the volume of the sphere in the first octant below y is equal to 8. Right? Now we are giving the limit of y is equal to x and y is z. Right. Now how to find this? Given is this vector given. Now we'll find the divergence of F. F by using Gauss theorem. Divergence of F is equal to del dot F. So this comes out to 1. So by the Gauss divergence theorem, surface integral of F dot n ds is equal to volume integral of divergence of F. AV, right? So this is equal to how much? F dot P. So F dot P comes out to 1. 1. V is equal to, this is the we have converted the whole volume into small cuboids of length, breadth, and height, dx dy dz. So this is equal to 1 dv over this dx dy dz. Now limits of this is equal to, now this y is from 0 to 8 given, y 0 to 8, and this is equal to, and z is equal to from 0 to 3. Z is equal to, this is equal to z is equal to 0 3. This is not, this should be z square. 0 to 3 and 0 to 3 and this x will from 0 to 3 and y from 9, z will from 0 to root of 9 minus x square. Okay, z square not y square, right? So now this become a integral scale point function. The integral of scale point function, which the triple integral you have calculated in the previous problem. Now they are we don't have any single term, so we can separately find them. Integral of this 1 to 8 of dz into integral of 0 to 1 dx, integral from 0 to, no, this x is here. So x here, you have to invert this to z first, then del of x, then x, because limit is not constant here. So you have to go into z, then x, then so this is z. Limit, upper limit, lower limit. Now differential of this to x. X will be now formula. Now you substitute the formula. Integral upon root of a square minus x square dx is equal to x into root of a square minus x square 2 plus a square by 2 sin inverse x. Substitute the value. So after substituting the value, put upper limit and lower limit. Upper limit is 3 0, upper limit 3 sin inverse 1. Right? This is 9 by 0 minus lower limit. This is equal to 0, 0, this is equal to 0, and this is equal to 0, and inverse is equal to 0. So 0, now you look with this, and this value is equal to 8 into sin inverse of 1 equal to 5. Now, this is the seed. When you calculate this surface into volume integral, this problem becomes easier. If you want to calculate this problem in surface integral, so it's very difficult to decide the surface here. So this problem becomes easy. This substitute f in the normal component of long component becomes easy if you come into volume, right? So that's how this cost dimension theorem helps in finding the surface integral over a fixed volume. Evaluate the integral. Evaluate the surface integral, surface integral of this, surface integral of f dot n vector ds, where f vector is this xy iota plus yzj minus zxk, where s is the surface of the cube bounded by the planes x0, x2, y0, y2, z0, z2. We are given this. This is a cube, right? Now f is given. We have to calculate the surface integral. This means, what do you mean? This means this. Write this, ds is here. So this means this. Integral of f dot dn is equal to surface integral of f dot n vector ds. Surface. Right? So this is a figure. The figure. Surface of the cube have 6 faces, and which are piecewise smooth. Each face, 6 faces are piecewise smooth. Problem. will become quite lengthy if we calculate the surface integral over the six faces. So to calculate this face, back face, and six faces, and add them, that will be the surface integral. Because if we draw the line parallel to any of the coordinate axes that will meet the surface at more than one point, therefore we cannot find the surface integral by projection on any of the coordinates, right? Therefore by the Gauss divergence theorem, surface integral is equal to of f dot is equal to volume into divergence of f. Now f is given, find divergence of f. Substitute y minus z minus y plus z minus x. Substitute the value. Limit is given as 0 to xy. Is from v is the value from 0 to x is 0 to 2, y is 0 to z. 0 to 2, 0 to 2, 0 to 2, x, y, z. Now this becomes a scalar point function, perpendicular scalar point function. So if is 0 to x, y is the constant, then substitute upper limit, lower limit, then x eliminated, then integrate with so y, predict z constant, put upper limit, lower limit, then this way z upper limit. This gives the surface conveniently before calculated. Otherwise you have to calculate the surface of six faces and then add them. This will give the values, right?